And so welcome to our final lecture, dealing with transition metal and coordination chemistry. And we had started talking about ligand field theory. The idea is we have at the center of the complex a metal, usually a metal cation. And it's not a hard sphere. When we were talking about crystal structures, we treated it like a hard sphere, but it's not a hard sphere. It's actually the metal center surrounded by its electrons moving in their orbitals as part of the electron cloud. The ligands acting as Lewis bases are therefore contributing electron density to that metal center. And we are starting to discuss what would happen when this electron density was added to the orbitals around the metal that already had electrons in them. For the s and p orbitals, the presence of the 6 ligands in an octahedral complex simply has the effect of shoving the energy of the s and the p orbitals higher. It has a fairly uniform effect and doesn't have any significant change. The case is different for the d orbitals because of the orientation of the orbitals in relation to the axes. The 6 ligands coming down the axes are interacting with the 5 orbitals differently. 3 of the orbitals, the dxy, the dyz, and the dxz orbitals, are actually in the quadrants. They basically have no presence along the actual axes. Those are nodes. And so the ligands are having almost no interaction with those 3 orbitals. The remaining 2 orbitals, on the other hand, it's completely different. The dx squared minus y squared are again straight down the axes. The ligands coming in interact directly with those 4. And in the same way, the dz squared is heavily oriented along the z-axis, so those ligands interact strongly, and it has a belly ring that is also interacting in the xy plane. So those 2 orbitals are shoved up in energy, whereas the other orbitals are relatively lower in energy. And so we have created an energy gap within the d orbitals. How big that energy gap would be would depend on how strongly the ligands interact with the metal centers. The more electron density the ligands shove into those orbitals, the bigger the gap is going to be. And it takes energy to move the electrons from one side of that gap to the other. And that, of course, is what we said. The moving the electrons across that gap is what produces the colors, because it takes energy, and the energy of that gap is in the visible light range. And so we have what is known as the spectrochemical series, based on how good the ligands are at actually pumping electron density into those orbitals. The ones that do the weakest interaction are at the bottom of the list. The ones that produce the strongest interaction are at the top of the list. And so we can see a wide range. For example, we can look at 4 complexes of chromium plus 3 with fluoride ligands, water ligands, nitrogen ligands, and cyanide as the ligands. The fluorides, of course, are poor ligands, and so the energy gap in the chromium, which has 6 fluoride ligands, is 4.6 times 10 to the 14th hertz. Water is a better ligand. The energy gap there is 5.2 times 10 to the 14th hertz for its frequency. For chromium ethylene diamine, it's nitrogens that are ligands, and nitrogens tend to be better ligands. 6.69 times 10 to the 14th is the frequency of the light absorbed there. And finally, cyanide, which is a very strong ligand, produces the largest gap at 7.98 times 10 to the 14th hertz. So we see that the colors produced by the complexes are related to how big this energy gap is. What other consequences do we run into as a result of this energy gap? Well, the whole point is we're getting this effect because of the electrons that are in the d orbitals. So what are the electrons that are in the d orbitals doing for these metal compounds? So where do the electrons go in our split level of Ds? Well, if we have just one d electron, it's obviously going to go into one of the bottom 3 orbitals because they're lowest in energy. The same thing for a d2, they're both going to go down. But of course they're going to try and avoid pairing because electrons avoid pairing whenever they can. And finally the d3, they'll spread all the way across. The interesting case shows up when we get to d4. We have 2 possibilities. Either the electrons can simply continue to stay unpaired and one of them go into the upper level, or they could end up going paired and end up in the lower level. And what's going to happen? Well, that brings us to the idea of pairing energy. It takes energy to push the electrons together. They don't like to do it. And so the question is it better for the electrons to go to the upper orbital and get higher in energy that way, or to pair up in the lower orbital and have its energy go that way? Well, that depends on how big that gap is. The larger the gap is, the more likely the electrons are going to want to go down in spin. We talk about the low spin case. The smaller gap, it's more likely to jump into the higher one, and we get what is known as the high spin case. So what we see happening is 2 possibilities. Where the gap is small, the electrons will tend to not pair. They'll want to go up into the higher orbital. We talk about the weak field case. Where the interaction with the ligand is strong, the pairing energy is going to be less than the energy gap, and all the electrons are going to end up in the lower set of orbitals. We talk about the strong field case. The reason this is significant, of course, is in the weak field case, we have 4 unpaired electrons. In the strong field case, we only have 2 unpaired electrons. And so there's a different magnetic susceptibility for these 2. They have different numbers of unpaired electrons. That's going to have significant properties as far as their magnetic behavior is going. In the D5 case, we again, all 5 can spread out, or they can go up, they can all be pushed down. Again, high spin, low spin case. D6, we have 5 orbitals filled. Now in the D6 case, we absolutely have to have pairing, and even in the weak field case. And in the strong field case, everything is paired. The weak field case has 4 unpaired electrons. The strong field case has no unpaired electrons. Totally different behavior. D7, we again have different numbers of unpaired and paired electrons. And when we get to D8, we again have just one form. Doesn't matter whether it's strong or weak field. And the same case for the D9. It doesn't matter if it's strong or weak field. So we see in the octahedral case, the strength of the ligand's interaction with the metal center can not only change the colors of the ligands, it can also change their magnetic susceptibility. That is, how many electrons are actually ending up paired. And that's a general rule for our octahedral complexes. Now we have to take into account the other possibilities we've discussed. That is, the tetrahedron and the square planar. In the octahedral case, the ligands have the effect of sending 3 of the orbitals lower in energy, 2 of the orbitals higher energy. Fascinatingly enough, the tetrahedral arrangement reverses that. It's the 3 orbitals that end up going higher in energy and the 2 going smaller. And you'll notice that that gap is smaller. Generally speaking, the interaction between the tetrahedron is only about 2/3 as great as it is for the octahedron, both because the ligands tend to be not as good, strongly interacting, and of course there's fewer of them. The last case, the square planar, splits the orbitals into 4 different groups, depending on the interaction. And generally speaking, you only see the square planar arrangement for D8 or D9 electron configurations, and it's only that top gap that ends up seeing splitting, the lower ones being full of electrons. And that concludes our discussion of coordination in transition metal chemistry. We've accounted for the colors and the different magnetic susceptibilities that complexes have. And that concludes the inorganic course for spring 2020 with Dr. Petty. Go have a nice summer.